In today's video, we'll learn about heat and internal energy. We define heat as the energy transferred between a system and its environment due to a temperature difference between them. We can measure heat in the units of calories, which is the amount of energy necessary to raise the temperature of 1 gram of water from 14 degrees Celsius to 15 degrees Celsius. As humans, we measure our energy consumption in kilocalories, which can be symbolized by a capital C. And we see that 1 kilocalorie is actually equal to 1,000 calories, and that 1 calorie is equal to 4.186 joules of energy. And since heat is energy transferred between a system, we see that internal energy is the energy associated with the atoms and molecules of the system. The internal energy includes kinetic and potential energy associated with the random translational motion, rotational motion, and vibrational motion of the particles that make up the system, and that any potential energy bonding the particles together, which we can see is summarized in our figure at the bottom right. If we look at our other figure to the right, we see that heat transfer is transferred from a high concentration to an object with a lower concentration, and that this process will proceed forward towards the cooler object until thermodynamic equilibrium is reached, where our heat transfer is then equal to 0. So we saw on the last slide that we measured the specific heat of water, which was the energy required to raise 1 gram of water by 1 degree Celsius. However, each substance requires a unique amount of energy per unit of mass to change the temperature of the substance by 1 degree Celsius. So if a quantity of energy is transferred to a substance that has a particular mass and its temperature is changed, the specific heat of the substance can be defined by taking the quantity of our energy divided by the mass of our material multiplied by our change in temperature. And we see that specific heat is symbolized by lowercase c, and its SI units are joules per kilograms degrees Celsius. If we want to find the energy required to raise the temperature of a system of mass by changing its temperature, we can measure it as our energy required is equal to the mass of our material multiplied by its specific heat multiplied by the change in temperature. If we're given a positive Q and we see that our temperature increases, therefore we can say that energy is flowing into the system. If we see a negative Q and our temperature is decreasing, then we see that the energy is flowing out of the system. In order to determine the specific heat of a substance, we use a calorimeter, which is a vessel that is a good insulator, which allows a thermal equilibrium to be achieved between substances without any energy lost to the environment. And since this system is isolated, the energy transfer from the warmer substance equals energy gained by the cooler substance, which is water in this case. As mentioned before, we see that each material has its own unique specific heat. And in our table to the right, we see we have some specific heat of some common materials that we use to measure the amount of energy required to raise the temperature of the system. In our first example, we're asked how much energy is required to raise the temperature of 1.5 kilograms of cadmium from 20 degrees Celsius to 150 degrees Celsius. And we're given that the specific heat of cadmium is equal to 232 joules per kilograms degrees Celsius. So if we summarize the information we're given, we see that we have a mass of 1.5 kilograms, and our material has a specific heat of 232 joules per kilogram degrees Celsius, and a change in temperature from a final temperature of 150 degrees Celsius minus our initial temperature of 20 degrees Celsius. which is a change in temperature of 130 degrees Celsius. And we're asked to find how much energy is required. So we're trying to solve for Q. The equation we can use to solve for Q is our mass multiplied by our specific heat multiplied by our change in temperature. Since we know 3 out of the 4 variables, we can solve for our Q. You see that the mass of our material was 1.5 kilograms multiplied by the specific heat of 232 multiplied by our change in temperature, which ended up being 130 degrees. When we calculate this out, we see that the energy required to raise 1.5 grams of cadmium from 20 degrees Celsius to 150 degrees Celsius is 4.52 times 10 to the 4th joules. In our second example, we're given a 75 gram sample of silicone at a temperature of 25 degrees Celsius. If 750 calories of energy is transferred into the silicone, what is its final temperature? And we're given that the specific heat of silicone is equal to 0.703 joules per gram degrees Celsius. So we can summarize the information we're given. We're given a mass of silicone, which is equal to 75 grams, an initial temperature of 25 degrees Celsius, and the amount of energy put in the system was 750 calories with a specific heat of 0.703 joules per gram degrees Celsius. And so we can use our equation where Q equals our mass multiplied by specific heat multiplied by our change in temperature. So since we're trying to find our final temperature, we can rearrange the equation. It will be equal to Q divided by MC plus our initial temperature. And since our energy is given to us in calories, and it must be in the form of joules, we can convert our 750 calories into joules by knowing that for every 1 calorie, there are 4.186 joules. So we see that our calories will cancel, and we'll be left with a value of 3,139.5 joules of energy. Now, if we plug in our joules of energy in for Q, we can solve for our final temperature. So 3,139.5 joules divided by our mass of 75 grams multiplied by our specific heat of 0.703 plus our initial temperature of 25 degrees will give us a final temperature that is equal to 85 degrees Celsius.